Somewhere in Wuxi, China, engineers just finished wiring a chip into a data center that most Western analysts did not think was possible to build for at least another 5 years. It is not a normal processor. It does not run on electricity in the way every chip inside your laptop, your phone, or every server humming away inside American tech companies does. It runs on light. Photons stream through etched glass pathways instead of electrons pushing through silicon. And according to the team that built it, this chip is now plugged directly into real AI data centers, boosting processing speed for certain complex tasks by a factor of 1,000. Not 1,000%, 1,000 times. And while American headlines have spent the last few months obsessing over GPU shortages and chatbot benchmarks, China quietly moved a genuinely novel piece of hardware from a research lab bench into actual operational infrastructure, running real workloads in aerospace, biomedicine, and finance. If that sentence does not immediately sound alarming to you, stick around, because by the end of this video it probably will, and I want to walk you through exactly what happened, how real it actually is, and where the United States genuinely stands in response. Let's start with the chip itself, because the technical details matter here and they are genuinely impressive, not just marketing fluff dressed up for a press release. This photonic quantum chip was developed jointly by two Chinese research groups, an institute called the Chip Hub for Integrated Photonics Explore, known as ChipEx, based in Wuxi in eastern China, and a company called Turing Quantum, founded by a physics professor at Shanghai Jiao Tong University. The chip earned a leading technology award at the World Internet Conference in Wuzhen, selected from more than 400 candidate technologies submitted across 34 different countries, which gives you some sense of how seriously the international scientific community, even outside China, is taking this particular achievement. What makes the chip technically remarkable is something called co-packaged photonics and electronics, essentially combining light-based quantum processing components with traditional electronic components on the same physical chip, at true chip-level integration, and doing it using wafer-scale mass production. According to the lead researcher on the project, this represents a genuine world first, being the first time anyone has achieved this specific combination of photonic and electronic co-packaging at a manufacturing scale ready for actual mass production, rather than a single fragile prototype sitting in a university lab. That distinction between a lab prototype and something ready for mass production is the entire crux of why this story matters so much more than yet another quantum computing headline. Quantum computing news has become almost background noise at this point. Another lab somewhere claims another record. Another qubit count gets announced, and most of it stays firmly locked inside research facilities, years or even decades away from touching anything resembling a real operational system that ordinary businesses or governments actually depend on. This is different. The pilot production line associated with this chip is reportedly capable of producing 12,000 6-inch wafers annually, and the chip itself is already deployed right now inside real facilities, serving aerospace, biomedical research, and financial applications, providing what its developers describe as computing power support that exceeds the limits of classical computers for specific specialized tasks. Now, before we go further, I want to be genuinely honest with you about something, because a good analysis of a story like this requires being straight about the limitations, not just the eye-popping headline numbers. That 1,000-fold speed claim is real, based on the reporting available, but it applies specifically to certain kinds of specialized computational tasks, not general-purpose computing across the board. Independent analysts covering this story have specifically flagged that key uncertainties remain around performance stability, error behavior over sustained operation, and how broadly deployable this technology actually is outside the narrow set of tasks it currently excels at. In other words, this is not a chip that suddenly makes every Chinese AI data center 1,000 times faster at everything they do. It is a chip that provides massive, genuinely useful acceleration for a specific category of complex computational problems, the kind that show up in aerospace simulation, drug discovery modeling, and certain financial calculations, while ordinary everyday computing tasks continue running on conventional hardware exactly as they always have. That distinction matters, and any analysis that skips over it in favor of just repeating the flashiest number available is not giving you the full picture. But even with that honest caveat firmly in place, the underlying achievement here is still genuinely significant, and here's why. This chip is not an isolated curiosity sitting alone. It arrived as part of a much broader, coordinated wave of quantum computing announcements coming out of China over just the past several months, each one reinforcing the same underlying story, that China is not simply doing quantum research anymore, it is actively integrating quantum technology into real operational computing infrastructure at a pace that has caught a lot of Western observers off guard. Just weeks before this photonic chip made headlines, China's home-developed Origin Wukong superconducting quantum computer, based at a research center in Hefei, announced it had preliminarily acquired the capability to support artificial intelligence computing directly, launching multiple quantum AI tools built specifically around that integration. Around the same period, researchers at Zhejiang built what they described as the world's first superfast quantum memory system, solving a critical data reading bottleneck that had previously slowed down even the fastest experimental quantum machines whenever they needed to process large volumes of ordinary classical data. Individually, each of these might read as a modest, incremental research milestone. Stacked together within the same several-month window, they paint a picture of a country systematically closing the gap between quantum research and quantum infrastructure, methodically, on multiple fronts simultaneously, rather than betting everything on a single flashy breakthrough. This did not happen by accident either, and if you want to understand why China is moving with this kind of coordinated intensity right now, you have to look at the policy driving it. Earlier this year, China unveiled its 15th five-year plan, the country's central economic and technological blueprint covering 2026 through 2030, and quantum technology sits explicitly at the very top of the list of priority future industries the government identified, alongside biomedical research, hydrogen and nuclear fusion energy, brain-computer interfaces, embodied artificial intelligence, and sixth-generation telecommunications. This is not a vague aspirational mention buried on page 200 of some bureaucratic document nobody reads. The plan specifically calls for expanded investment in scalable quantum computers, the creation of hyperscale computing clusters powered by massive dedicated electricity supplies specifically designed to train advanced AI models, and the construction of an integrated space-to-Earth quantum communication network, an enormously ambitious infrastructure project linking satellites and ground stations together using quantum encrypted communication. When a government with the kind of centralized planning power China has puts a technology at the very top of its national priority list like this, it tends to translate into exactly the sort of coordinated multi-front progress we have been watching unfold over the past several months. The funding numbers behind this push are genuinely staggering once you actually look closely at them, and this is where the American side of the story starts becoming impossible to ignore. According to a widely cited scorecard from the Special Competitive Studies Project, an organization focused specifically on tracking U.S.-China technology competition, China has committed more than double the government funding. The United States has put toward quantum information science and technology over the past 7 years, roughly $15 billion in Chinese state funding compared to approximately $6 billion from the American government over that same window. Other estimates put China's public quantum investment figure closer to $18 billion, still comfortably outpacing American government spending in the same category by a wide margin. And critically, the way that money flows is structurally different between the two countries in a way that genuinely matters. In China, quantum funding flows directly from the top levels of central government down to specific research institutions and priority projects, creating intense pressure on China's leading quantum researchers to deliver high visibility results in order to keep attracting that state backing. In the United States, quantum funding has historically been far more decentralized, spread across federal programs like the National Quantum Initiative, agencies including DARPA and the Department of Energy's national laboratories, but relying much more heavily on private venture capital, university research budgets, and individual company investment decisions, rather than one single coordinated national funding stream. So does that mean America genuinely has no answer here? The way the more provocative headlines about this story tend to frame it, the honest answer is more complicated and more interesting than a simple yes or no, and it is worth actually sitting with the nuance rather than reaching for the easy, dramatic conclusion. Just this past May, the United States government made its most significant direct move yet in this space, when the Department of Commerce announced letters of intent distributing just over $2 billion in direct funding to 9 American quantum computing companies under the CHIPS and Science Act, with the federal government taking an actual minority equity stake in each recipient company, an approach that mirrors industrial policy strategies more commonly associated with how China itself funds strategics, technology sectors. This was a genuinely notable shift, representing the American government moving from its traditional posture of funding research and letting private markets sort out the winners towards something that looks much more like direct, deliberate national industrial strategy, specifically targeting quantum computing as a matter of both economic competitiveness and national security. The market reaction alone tells you how significant this was interpreted to be. American quantum computing stocks absolutely exploded following the announcement, with shares of companies like Rigetti Computing jumping more than 63%, D-Wave surging roughly 53%, and Inflection soaring more than 30%, all within just a couple of trading days. And in a fascinating twist that tells you everything about how intertwined this competition has become, Chinese quantum computing stocks rallied too, immediately after the American announcement, as investors correctly anticipated that Beijing would respond with its own accelerated push to maintain its lead, which is exactly the kind of tit for tat escalation pattern you would expect to see in a genuine technological arms race between two major powers. So where does that actually leave the balance of power right now, as of the middle of this year? According to the same Special Competitive Studies Project analysis, the United States still maintains what the report describes as a narrow overall lead over China across quantum technologies broadly. But that lead is genuinely narrowing. And the two countries are actually strong in noticeably different areas rather than one side simply dominating across the board. The United States retains clear advantages in quantum software, error correction research, private capital investment, and significant portions of the broader supply chain, while China has pulled ahead, specifically in quantum networking deployment, and is actively closing the gap in materials science, manufacturing capability, and talent development. To put some concrete numbers behind that software advantage specifically, data from December of last year showed IBM's popular quantum programming toolkit called Qiskit had accumulated more than 450,000 downloads globally, compared to roughly 4,000 downloads for China's comparable domestic software development kit. That is a massive gap in developer ecosystem adoption, suggesting that even as China races ahead on manufacturing and deployment, the actual global community of programmers and researchers building quantum applications still leans overwhelmingly toward American-developed tools and platforms. Similarly, American entities have reportedly deployed somewhere between 39 and 73 operational quantum computers, compared to an estimated 15 to 18 in China, another area where sheer numbers still favor the United States for now. But here is exactly why the specific story about this photonic chip integrated into real AI data centers should genuinely worry anyone tracking this competition closely, even against that broader backdrop of America still holding a narrow overall lead. Software ecosystems and raw deployment counts matter enormously for long-term competitiveness, but they matter less in the short term than the specific, narrower question of who actually gets working operational quantum-enhanced infrastructure into real production environments first. China did not just publish an impressive research paper about photonic quantum computing theory. It built a manufacturing pipeline capable of producing 12,000 wafers a year, and it plugged the resulting chips directly into data centers already running real workloads for real industries. That is a fundamentally different kind of achievement than a laboratory demonstration. And it is exactly the kind of achievement that tends to compound advantages over time, because operational deployment generates real-world performance data, uncovers practical engineering problems that only show up at scale, and builds the kind of institutional manufacturing expertise that is extremely difficult for competitors to quickly replicate once a rival has established a working production pipeline and a head start on real deployment experience. There's also a structural piece of this puzzle worth understanding, because it shapes exactly why China has been able to move as quickly as it has in recent months on the manufacturing and deployment side specifically, even while lagging in raw software ecosystem size. China's broader AI data center buildout has faced real, well-documented constraints over the past year, driven significantly by American export restrictions, limiting Chinese access to the most advanced American-made GPU chips, the workhorse processors, currently powering the overwhelming majority of AI training and inference around the world. Reports indicate that out of an originally budgeted $400 billion in planned 2025 capital expenditure by major Chinese technology companies building AI infrastructure, only about half of that was actually able to be deployed during the first 3 quarters of the year, specifically because of these chip export restrictions, combined with an ongoing lack of sufficiently advanced domestic alternatives. In a strange, almost paradoxical way, that very constraint may have actually accelerated China's push into photonic and other alternative quantum-adjacent computing approaches. When you cannot simply buy your way to more computing power by purchasing the latest cutting-edge American GPUs, you have significantly stronger institutional incentive to pour resources into fundamentally different computing architectures that do not depend on the same restricted supply chains, and photonic quantum chips, built domestically using China's own manufacturing capabilities, fit that strategic need almost perfectly. This is not something Chinese planners are likely to publicly frame this way in official statements, but the timing and the strategic logic line up too cleanly to be pure coincidence. If you find this kind of behind-the-scenes look at how global technology competition is actually unfolding valuable, go ahead and hit that like button right now. It genuinely helps this channel reach more people who want the full, nuanced picture rather than just alarmist headlines. And if you want to keep tracking exactly how this quantum and AI race between major world powers develops from here, subscribe, Because based on the pace of announcements over just the past several months, this story is only going to keep accelerating. There is another dimension of this competition worth understanding, one that rarely makes it into the flashier headlines about chip speeds and data center integration. And that is the talent question sitting underneath all of it. Building working quantum hardware, let alone integrating it successfully into real production infrastructure the way China's photonic chip has apparently achieved, requires an extremely specific, extremely scarce combination of expertise spanning quantum physics, advanced materials, science, precision manufacturing engineering, and increasingly machine learning and AI systems design as well. There are simply not very many people on Earth who genuinely understand all of these disciplines well enough to contribute meaningfully to a project like this, and both countries are competing intensely for that same tiny, highly specialized global talent pool. China has invested heavily in domestic quantum education programs, expanding graduate research positions at institutions like Shanghai Jiao Tong University, the very institution where Turing Quantum's founder holds his professorship, specifically to grow a homegrown pipeline of quantum specialists, rather than depending on attracting foreign-trained researchers. The United States, meanwhile, has historically benefited enormously from its ability to attract top international quantum research talent to American universities and companies, a long-standing advantage built on decades of world-leading academic institutions and generous research funding. But that advantage is not guaranteed to persist indefinitely, particularly as visa policy debates, geopolitical tensions, and increasingly attractive research opportunities and funding levels back in China itself start pulling some of that talent in different directions than it might have flowed a decade ago. Several American quantum researchers and industry leaders have publicly voiced concern in recent years that the United States risks losing its traditional talent advantage if it does not continue investing aggressively in both attracting international researchers and training more homegrown quantum specialists through its own university system. It is also worth spending a moment on quantum sensing specifically, a close cousin of quantum computing that tends to get far less media attention, despite carrying arguably even more immediate strategic and military significance than the computing side of this competition. Quantum sensors exploit the same strange underlying physics as quantum computers, superposition and entanglement, but instead of performing calculations, they use those properties to detect incredibly subtle changes in gravity, magnetic fields, and electromagnetic signals with a level of precision that classical sensors simply cannot match. Practical applications include detecting submarines hidden deep underwater with far greater precision than current sonar and magnetic detection methods allow, building navigation systems that do not depend on GPS satellites at all, which matters enormously in any contested military environment where an adversary might attempt to jam or spoof satellite signals, and enabling early detection of underground facilities, mineral deposits, or structural changes that would otherwise remain completely invisible to conventional sensing technology. China has invested heavily and specifically in quantum communication and sensing infrastructure, including an ambitious, genuinely unprecedented plan to build an integrated network linking quantum-secured satellites with ground-based stations, part of the same 5-year plan that placed quantum technology at the very top of the country's strategic priority list. This particular piece of the broader quantum race receives far less mainstream media coverage than headline-grabbing computing benchmarks, but multiple defense analysts consider it potentially even more consequential in the near term, since useful quantum sensing applications appear to be arriving on a faster practical timeline than fully fault-tolerant, broadly useful quantum computing. Let's also take a moment to place this current moment in some useful historical context, because emerging technology races between major world powers are not actually a new phenomenon, even if the specific technology involved, photonic chips and qubits, feels unfamiliar and futuristic. The most obvious historical parallel that keeps coming up in serious policy discussions is the original space race between the United States and the Soviet Union during the 1950s and 60s, where a single, highly visible technological achievement, the launch of Sputnik, triggered a massive, sustained wave of American government investment and urgency that had been comparatively lacking beforehand. Some policy analysts have started explicitly describing China's recent run of quantum breakthroughs, this photonic chip integration very much included, as a potential Sputnik moment for quantum computing specifically, a sufficiently dramatic, sufficiently visible achievement that could galvanize a similarly large-scale, sustained American policy response rather than the more incremental, distributed funding approach that has characterized American quantum investment up until quite recently. Whether that comparison ultimately proves accurate remains to be seen, but the fact that serious policy analysts are reaching for that specific historical parallel tells you how seriously at least some segments of the American national security and technology policy establishment are taking this recent wave of Chinese quantum announcements. There's a meaningful difference worth acknowledging between the original space race and this current quantum competition. Though, and it is worth being precise about it rather than assuming the historical parallel holds perfectly. The space race played out largely as a single, highly centralized government program on each side. NASA facing off against the Soviet Space Agency with clear, easily measurable milestones like who reaches orbit first or who lands on the moon first. The quantum race looks structurally different on both sides. Even within China's more centralized state-directed model, multiple different institutions, ChipEX, Turing Quantum, the Anhui Quantum Computing Engineering Research Center behind Origin Wukong, and various university labs are all pursuing meaningfully different technical approaches simultaneously, superconducting qubits, photonic qubits, and other experimental architectures, rather than one single unified national program pursuing one single technical path. And on the American side, that diversity is even more pronounced, spread across dozens of competing private companies, university labs, and federal research programs, each pursuing its own particular bet on which underlying quantum hardware approach will ultimately prove most scalable and commercially viable. This messier, more fragmented competitive landscape makes the quantum race considerably harder to track with a single simple scoreboard than the original space race ever was, but it also means that predicting a single decisive winner, the way we eventually got a clear answer about who reached the moon first, may simply not be the right mental model for how this particular competition ultimately resolves. It is also worth being honest about a genuine methodological challenge running through nearly every comparison being made in this entire conversation, one that responsible analysts openly acknowledge even as they continue tracking this competition closely. China's government-linked research announcements, including this photonic chip story itself, are considerably harder for independent outside observers to fully verify compared to announcements coming from American companies, many of which are publicly traded and therefore subject to considerably more rigorous disclosure requirements, external audits, and scrutiny from independent financial analysts with direct financial incentive to catch any exaggerated or misleading claims. That is not meant to suggest Chinese quantum achievements are somehow fabricated or fundamentally untrustworthy. The underlying research clearly involves real institutions, real published technical details, and international recognition through awards like the one this specific chip received at the Wuzhen Summit. But it does mean that responsible, careful analysts generally apply a somewhat more cautious, wait and verify posture toward headline claims coming out of Chinese state-linked research announcements specifically, compared to claims made by American companies that face direct market consequences, shareholder lawsuits, and reputational damage, if their public claims turn out to be significantly overstated or misleading. This caution should not be mistaken for dismissiveness. It simply reflects a reasonable measured difference in how transparently verifiable each side's specific claims tend to be, given how differently the two countries structure disclosure and independent oversight around strategically significant technology announcements like this one. It is worth addressing directly the comparison several outlets covering this story have leaned on. The claim that this photonic chip runs certain workloads up to 1,000 times faster than a leading NVIDIA GPU, since NVIDIA's chips remain the dominant global benchmark for AI computing power that most audiences intuitively understand. That comparison, while attention-grabbing, deserves the same careful scrutiny as the broader speed claim itself. NVIDIA's GPUs are general-purpose accelerators, extraordinarily good at an enormous range of AI training and inference tasks precisely because of that generality, while this photonic chip appears to excel specifically within a narrower band of specialized computational problems suited to how photonic processing actually works at a physical level. Comparing the two directly, as several headlines have done, is a little like comparing a Formula One race car to a heavy-duty freight truck, and declaring one simply faster than the other without specifying what exactly is being hauled or raced. The race car will win on a smooth, well-suited track every single time, but ask it to haul 40 tons of cargo across rough terrain, and the comparison falls apart immediately. None of this means the underlying achievement is not real or not significant. It clearly is, but the most responsible way to read these comparisons is as evidence of a genuinely powerful new tool for specific, well-suited tasks, not as evidence that Chinese hardware has simply leapfrogged the entire American semiconductor industry across the board in one single announcement. Let's talk about what actually happens if this trajectory continues roughly the way it has been unfolding, because the implications extend well beyond simple national pride or bragging rights about who built the more impressive chip first. Quantum-enhanced computing infrastructure, once it genuinely matures and scales, carries enormous implications across nearly every strategically important sector you can think of. In finance, quantum-accelerated computation could meaningfully speed up complex risk modeling, fraud detection, and algorithmic trading strategies. potentially giving whichever country's financial institutions gain access to this capability, first, a genuinely measurable edge in global markets. In biomedicine, faster molecular simulation and drug discovery modeling could compress years off pharmaceutical development timelines, a capability with obvious economic value, but also significant public health and even biosecurity implications, depending on exactly what gets developed and by whom. In aerospace and defense specifically, faster simulation capabilities directly translate into faster design cycles for everything from aircraft components to missile systems to satellite communication networks, exactly the kind of dual-use technology that shows up in both civilian industry and military applications simultaneously, which is precisely why governments on both sides of this competition treat quantum computing as a matter of core national security, rather than simply an interesting scientific curiosity worth funding for its own sake. It is also worth pointing out that this entire race is unfolding against a backdrop, where the practical usefulness of near-term quantum computing remains a genuinely open, actively debated question among serious researchers. And it is worth being honest about that uncertainty rather than pretending the outcome here is already settled. Most credible industry roadmaps, according to analysts tracking the sector closely, still place the point where quantum systems begin delivering unambiguous, broadly recognized commercial value somewhere in the 2028 to 2032 timeframe, several years out from where we currently stand. Some prominent voices in the industry have become noticeably more confident recently, with certain analysts now willing to state clearly that by 2029, quantum machines will be performing calculations that classical computers genuinely cannot replicate, a level of confident, specific timeline commitment that would have sounded wildly premature just a couple of years ago. That shifting confidence itself tells you something important about how quickly the underlying technology has actually been maturing. Even if full-scale, broadly useful commercial quantum advantage still sits a few years out on the horizon rather than having already fully arrived. There is a genuinely important structural difference worth returning to here as we wrap up, because it shapes how this entire competition is likely to keep playing out over the coming years, regardless of which specific country happens to be ahead on any given headline announcement in any given month. America's approach, spreading investment across competing private companies, universities, and multiple government laboratories, rather than concentrating resources under one centralized national program, has historically been a genuine source of strength for American technology development broadly. Producing more diverse approaches, more competitive pressure between rival companies pushing each other to innovate faster, and a genuinely deeper pool of available private risk capital willing to bet on ambitious, uncertain technology bets that might not pay off for years. China's more centralized, top-down model sacrifices some of that diversity and competitive pressure between rival approaches, but it gains something equally valuable in return: the ability to move with remarkable speed and coordination once national leadership has clearly identified a strategic priority. Precisely the pattern we have watched play out in quantum computing specifically over just the past several months. Neither model is simply better than the other in some abstract, universal sense. They represent two fundamentally different theories about how technological leadership actually gets built and sustained over the long run. And this particular quantum computing race happens to be one of the clearest real-world tests of those two competing theories currently playing out anywhere in the global economy. So where does this leave us, honestly, as we close this out? China did just connect a genuinely novel photonic quantum chip to real operational AI data centers, running real workloads across aerospace, biomedicine, and finance, and that achievement is real, independently verified by international observers, and genuinely significant, not empty state propaganda dressed up for headlines. But America has not simply sat on its hands watching this happen from the sidelines either. Having recently made its most direct, aggressive quantum investment move, yet through targeted federal funding paired with actual equity stakes in 9 leading American quantum companies, a genuinely significant shift in strategy that markets immediately recognized as meaningful. The honest, complete picture sitting underneath the more provocative framing of this story is that we are watching a genuine escalating technological race between two systems, with fundamentally different strengths. China currently pulling ahead on the specific, narrower question of translating quantum research into deployed manufacturing infrastructure and real production. America still holding a meaningful overall lead in quantum software ecosystems, private capital depth, and total number of deployed quantum systems, with neither side's advantage looking permanent or guaranteed to hold as this competition continues accelerating in the months and years directly ahead of us. Whoever ultimately translates quantum research into genuinely scalable, broadly useful, reliably operational systems first, across computing, secure communications, and precision sensing simultaneously, is very likely going to hold a significant strategic advantage for years afterward. And based on everything we have just walked through, that outcome remains a great deal more uncertain and a great deal more actively contested right now than most of the headlines currently circulating about this story would have you believe. What seems clear, regardless of exactly how the next few years of this competition actually unfold, is that the era of quantum computing existing purely as an abstract, distant research curiosity is quietly ending in real time. A chip built in Wuxi is running real workloads right now. Federal dollars are already flowing into 9 American companies with real equity stakes attached. Stock markets on both sides of the Pacific are already pricing in expectations about who wins this race, months or years before the technology itself has fully matured. Whatever you personally believe about which country ultimately comes out ahead, the days of treating quantum computing as tomorrow's problem, safely distant enough to ignore for now, appear to be over. The race is already underway. The scoreboard is already being watched closely by investors, policymakers, and defense planners alike. And based on the pace of announcements coming out of both countries over just the past several months, it does not look like it is slowing down anytime soon.